Today we're going to talk about arithmetic sequences and series. So we're just going to go back a little bit yesterday, and I picked a couple new patterns here for us to look at. So first of all, let's take a look at this A pattern. The first time I have 2, the second time 3, the third time 4, the fourth time 5, the fifth time 6. So what is occurring from term to term to term to term? Add 1, add 1, add 1, add 1. So if I repetitively add, that becomes 1n plus. When I put 1 in there, what do I have to add to it to get to 2? 1. I put 3 in there. 3 plus 1, 4. Yep. 5 plus 1, 6. Yep, it all checks out. But here, in section B, what am I doing from term to term to term? Times 2, times 2, times 2, times 2. So I repetitively multiply. I take my ratio to the n minus 1 times my first term. Now some of you might say this is just 2 to the n, and you're absolutely right. But let's take a look at this one right here. That is 2 to the first times 2 to the n minus 1. And when your bases are the same, what do you do with these powers? You add them, and 1 minus 1 is 0, so it does become 2 to the n in a simplified version. But you may always keep it in this sequential formula version. Now let's investigate a little bit more. When you first went to school, what did you learn first? How to do arithmetic, adding, subtracting, multiplying, or dividing? You learn how to add first, okay? Then, second of all, you learned how to multiply, agree? Now, which did you learn first? Arithmetic or geometry? Arithmetic. So would it make sense to you that when we repetitively add, we call that arithmetic? And when we repetitively multiply, we call that geometric. Because you learned arithmetic before geometry, and you learned to add before multiplication. Now let's take a look here. Common ratios, common differences. Which has a common difference from term to term to term? The arithmetic. Common difference of 1. So the common difference goes to the arithmetic. And in this specific example, we're going to call that common difference D, and in ours, D is 1. So the common ratio then must go to the geometric. And our common ratio in this case was the 2. We call the common ratio R. Now which of these involve a first term in their formula? Was 1 the first term here? No. Was 2 the first term here? Yes. So the first term belongs to the geometric. But let's see if we can see if the first term also belongs to the arithmetic. Up to this point, we have said the arithmetic is the common difference, which is repetitively adding, so that's dn. Plus some constant should give me my term, right? Isn't that what we did? 1 times 1 plus what gives you 2? 1 times 4 plus what gives you 5? I'm going to show you how you can get this constant back here. Let's see if it works. A sub 1 minus the difference. Let's see if I take this. take this first one. The difference was 1. 1 n. So 1 times 1 plus my first term is 2 minus my difference is 1. That becomes 1 plus 1. Does that give me my 2? Let's try the next one. 1 times 2 plus first term was 2 minus 1. 2 plus 1 give me my 3. So another way to write this, dn plus c, is a sub 1 minus d. And then we mathematicians like to take that just one step further, because these two have a d in them. So we would factor out that d, and we would have n minus 1. And we have plus the first term. And there is our rule for an arithmetic sequence. So an arithmetic sequence can also have a first term. But if you like to use this formula best of all, you may use that one. But do know it does lead to this formula if you're given the first term as well. And that's actually what I have hidden behind this little star. It's the general rule to an arithmetic sequence. Either the one in yellow or the one in pink. Let's try a few. First, let's just see if it is arithmetic or not. From -10 to -6, add 4. -6 to -2, add 4. -2 to 0, add 2. 0 to 2, add 2. Add 4, add 4. Are you constantly finding the same difference? No. The difference is 4 and 2. I must have just one difference. Let's try B. Add 6, add 6, add 6, add 6. Is that arithmetic then? Do you have the same difference all the time? Yes, my difference is 6. So yes, this is arithmetic. Let's see if we can now write the rule, just like we did yesterday. From 32 to 47. Add 15. From 62 to 47. Add 15. 62 to 77. Add 15. Do you have a common difference? Yeah, my common difference is 15. So it is arithmetic. So I would write the rule is 15n. So 15n plus what gives me my term? Well, let's see. We have the first term, so let's put a 1 in here for the n. And that first term is 32. So subtract 15. And what do you get? 17. So 15n plus 17 gets me my rule. Let's see if it works. When you put in your 2. 2 times 15 is 30, plus 17, 47. Let's try 3. 3 times 15, 45, plus 17, 62. So then what would a to the 12th be? Well, 15 times 12 plus 17. 15 times 12, 180 plus 17, 197. There's my 12th term. Let's try graphing it. The 8th term is 50, so I'm a blank person. 1, 2, 3, etc. to the 8th. And I have 50. The difference is 0.25. So from term to term to term, I add 0.25. So the next one would be 50.25. The next one would be 50.5. So can we write a general rule? Well, I know it is my difference times n. So 0.25n plus what? Question mark, or let's say c, some constant, gives me my term. I didn't have the first one, but I have the 8th one. So I'm going to say 0.25 times 8 plus what gives me that 8th term, which is 50. Well, a fourth of 8 is 2 plus what gives me 50? 48. So I can replace this c with a 48. And I have my rule. Let's see if it works. 0.25 times 9 is 2.25 plus 48, 50.25. It's working. Now let's graph this. I'm going to put a break in my graph, and I'm going to start at the first term. If I put a 1 in there, I get 48.25. Then 48.5, 48.75, etc., etc. So I'm going to start at 48. 0.25.5, 0.75, 49, 0.25.5, 0.75, 50. I'm going to kind of draw this one in because it's kind of faded out. 0.25, well, we can go up to the 8th term. So 1, 2, 3, 4, 5, 6, 7, 8. Looks like this 4th is also kind of, and the 6th kind of dazzled out. Okay, let's plot those in red. 1, 48.25. 2, 48.5. 3, 48.75. 4, 49. 49.25. 49.5. 49.75. 50. Is this looking linear? Is this a linear equation? Repetitive adding is linear. Alright, let's try this next example. 2 terms of arithmetic sequence. The 5th one and the 30th one. So I got to do my little picture. 1st, 2nd, 3rd, 4th, 5th is 10. All the way to the 30th is 110. Okay. Let's go back a minute. Notice here, I started with 32, then went to 47, and I said the difference between those was 15. And this was the first term. So if I take that, I have 15n. What is the 15 in this equation? It is the difference. And if you look at it as a linear equation, it is also the slope. So the difference is the slope of any arithmetic sequence. So let's go back here. Which are my x's? The 10 and 110 or the 5 and 30? These would be my x's and these would be my y's. So slope, the difference is slope, which is the difference of my y's, 110 minus 10, over the difference of my x's. 30 minus 5. 110 minus 10 is 100. 30 minus 5 is 25. 100 divided by 25 is 4. My difference is 4. So automatically, I know that's going to be 4n. Were you given the first term? No. So instead of putting in a 1, I need to put in the fifth term. So I need to put a 5 in here. So 4 times 5 plus what will give me 10, the fifth term. That's 10 equals 20 plus what? Subtract 20. That's negative 10 is my c. So I can replace this c with a negative 10. 4n minus 10 is my rule. Now part B says, find the value for which the term is negative 2. So the term of negative 2 equals what position? 4n minus 10. Add 10. 8 equals 4n. n equals 2. The second position is where negative 2 is located. Well, let's see. If I have a difference of 4, subtract 4 would be 6, subtract 4 would be 2, subtract 4 would be negative 2. Am I right? Well, it falls into place. Now I have a story to tell you about Carl Friedrich Gauss. When he was a little boy, he was a naughty little boy. He was such a smart little boy. And because he was so smart, it often made things difficult for his teachers. So, he was being kind of rambunctious one day, so his teacher said to him, "Little Carl Gauss here, going to call him Little Freddy. I want you to add up the first 100 numbers." Just thinking, this is going to take Freddy some time. After 3 minutes, 9-year-old Carl Friedrich Gauss said, "That is 5,050. The teacher said, "Oh my gosh, how did you do that? How did you figure that out?" And he said, "Well, let me show you. I knew I had to add up 1 and 2 and 3 and 4 and 99 and 100. So I figured I'd start lining this 100 up and start going backwards. What is 1 plus 100? 101. What is 2 plus 99? 101. 3 plus 98? 101. 101. But did he need 100 both times? No, he only needed half of that. So he said half of that would have been 50 times 101 is 5,050. So let's see what little Freddy Gauss did. Little Carl Friedrich Gauss. This is which term? The first term. Plus, this is which term? The last term. And we represent that as a sub n. And he added those two together. He didn't need 100, he only needed 50 of them. 50 is half of all the terms. And that is how he got the sum of an arithmetic sequence. N over 2 times a sub 1 plus a sub n. So let's try a few. Consider the series 20 plus 18 plus 16 plus 14. Right away, I start to look at this pattern. Subtract 2, subtract 2, subtract 2. So it repetitively would be a negative 2n. 2 times 1 is negative 2, plus what gets me to 20? 22. All right. We want the sum of the first 25. So according to that, the sum of 25 would be n over 2, half as many as I need, times the first term plus the last term. Well, I'm adding up 25 of them. My first term is 20, plus my last term, the 25th term. How can I find the value of the 25th term? Plug it into the rule. So negative 2 times 25 plus 22 should equal the 25th term. Negative 50 plus 22 should equal the 25th term. That is negative 28. So plus a negative 28. So what I have is 25 over 2 times negative 8. Negative 4 times 25, negative 100. That would be the sum of those 25 terms. Adds up to a 100. Now part B says, how about if you're given the sum is negative 760? How many terms does that take? Well, I know n over 2 times the first term plus the last term. I don't have the last term, but I have an expression for it. Negative 2n plus 22 should get it for me. So let's do some algebra. Multiply both sides by 2. That gives me negative 1520 equals n times 20 plus 22 is 42 minus 2n. That's negative 1520 equals 42n minus 2n squared. Let's put it all on one side of the equal. So 2n squared, add 2n, subtract 42n minus 1520 equals 0. There's a 2 in them all. So I'd have n squared minus 21n minus 760. Now I could try to factor factors of 760 that differ by 21, but that's going to take me a long time. I'm going to get there faster if I do the quadratic formula. So the opposite of b, which is a negative 21, so it would be 21. I'm going to do that over here. 21 plus or minus the square root of b squared minus 4. A is 1. C, negative 760, all over 2a. And a was 1. So that gives me 21 plus or minus square root of, let's see, 21 squared, 441 plus, because negative and negative, so 4 times 760, 3040, which is 21 plus or minus square root of 3481, which is 21 plus or minus, oops, no more square root, 59 over 2. Well, 21 minus 59 would be negative. I can't count negatively, so I have to do the positive. 21 plus 59 is 80 over 2 is 40. 40 terms. Okay. One more of those. Okay, from term to term to term, add 10, add 10, add 10. So that's going to be 10n. 10 plus what gets you to 100? Plus 90. Okay, so I want how many? 18 terms, so A. Sum of 18 will be 18 over 2 times the first term, 100, plus the last term, 18th term. So I got to figure that out. The 18th term, 10 times 18 plus 90, 180 plus 90, 270. So plus 270. Half of 18 is 9 times 370 is 3,330. Part B says, well, what if I give you the sum? How many terms is it? Well, my sum was 600. I don't know how many terms. The first term is 100 plus the last term. I don't know, but I have this expression, 10n plus 90. Multiply both sides by 2. And I get 1200 equals n times 190 plus 10n. That's 1200 equals 190n plus 10n squared. I'm going to move the 1200 over here. So I have 10n squared plus 190n minus 1200 equals 0. There's a 10 in them all. N squared plus 19n minus 120 equals 0. So again, I'm going to do quadratic. Opposite of b, plus or minus square root of 19 squared minus 4ac all over 2a. $361. Negative negative makes a positive. 480 all over 2. That is negative 19 plus or minus square root of 841 over 2. Negative 19 plus or minus 29 over 2. Again, that makes negative, so negative 19 plus 29 is 10 over 2, which is 5 terms. So that should give you the idea of how to use the arithmetic sum. Let's do one story problem, and then we can call it good. A construction company is laying natural gas pipeline. Several sections have been laid in a pile at the construction site. There are 12 sections of pipe in the bottom row. So here in this bottom row, I have 12 pieces of pipe. Each row has one less pipe than the row below it. There are 8 rows of pipe. So this is the bottom. So I have 8 rows. 1, 2, 3, 4, 5, 6, 7, 8. There are 12 sections of pipe in the bottom row. Each row has one less. So this would have 11, 10, 9, 8, 7, 6, 5. Write the rule. Well, what are you doing from term to term to term? Adding 1. Excuse me. Adding a negative 1. So that would be negative 1n. Plus what? So I put 1 in there, that's negative 1, plus what gets me to 12? Plus 13. Put a 2 in there, negative 2 plus 13, 11. Put a 5 in there, negative 5 plus 13, 8. Yep. So there's my rule. Part B says, which row has 6 sections of pipe? Well, if I look here, it's the 7th row. Let's see if we can mathematically calculate it. Which row has 6 sections of pipe? So the value is 6, negative 1n plus 13. Subtract 13. Negative 7 equals negative 1n. 7 equals n. Same as when we listed. So you see it mathematically as well as by the sequential listing. There are some problems to practice, and we can discuss any questions you have tomorrow.